Okay, so we're going to pick up where we left off. There's not too much left. With the theory aspect, anyway. The general solution to homogeneous systems is very similar to nth order differential equations. It's just going to be in matrix form. So if we let x1...
Please excuse this announcement. If you are doing Day 2 Prairie State Makeup, please go to room 135. Day 2 Prairie State Makeup, room 135.
If we let x1, x2, and so on be a fundamental set, which again, if you forgot, that means that the set is linearly independent on I, then the general solution to the system is exactly what we would expect. X equals C1x1 plus C2x2, just using the superposition principle, plus C3x3, so on. Okay. So from the previous example, which, let's see, we had x1 equal to 1 negative 1 e to the minus 2t, x2 equal to 3 5 e to the 6t. These were solutions for x prime equal to 1 3 5 3 times x. Bless you. So since x1, whoops, forgot my little vectors here. Since x1 and x2 are linearly independent, which we proved, I believe, at the end of class yesterday, using the Wronskian. The Wronskian was not equal to 0 for all t. Then we say that the general solution is x equal to c1 times 1 negative 1 e to the negative 2t plus c2 3 5 e to the 6t. And this is the general solution. Okay? Any questions on that? And the last bit of linking back to the theory that we've done before is the non-homogeneous aspect. So the solution is going to look something like this. We let x1, x2, and so on, up through x sub n, be a set of solution vectors of x prime equal to ax, and we're going to introduce x sub p, another solution vector, but it's the solution vector of x prime equal to ax plus f. By superposition, x equal to c1 x1 plus c2 x2 and so on, plus c sub n x sub n plus x sub p is also a solution. And just like before, if we have x sub c equal to c1 x1 plus c2 x2 plus c sub n x sub n, so that's the complementary solution of the system. If this is the general solution, to the homogeneous system, then x equals x sub c plus x sub p is the general solution to the non-homogeneous system. Okay. So this is pretty much a review of the theory that we knew earlier when we did nth order differential equations, applied now to systems of systems of differential equations using matrices. Hopefully this is more of a review, not anything too confusing. The last part of the section, we do kind of throw in a little bit more matrix theory, so this part is not something we've done before. Okay, so next item is a fundamental matrix so let's say we have x1 and so on, all these solution vectors. Let's say these are, or let's say this forms a set of solutions that are linearly independent, which of course means that it's a fundamental set. of x prime equal to ax. Then what we're going to do is kind of write out what all this stuff looks like and then introduce some different notation. So we know that the solution is going to be c1x1 plus c2x2 and so on. Whoops, that's not, I don't mean to do 3. I want that to be n. C sub n, x sub n. If we go ahead and actually write out what all these solution vectors look like and try to simplify the matrices, and here's what we get. Solution vector for x1 is going to be x11, x21, all the way down to x sub n1. It's going to have n rows, 1 column. And similarly, we can do that for each of them. x21, x22, xn2. Oh, whoops. Man, I'm messing up left and right today. This should be 1, 2. 2, 2. And 2. Plus C sub n. And then first row, nth column. Second row, nth column. Nth row, nth column. If I go ahead and actually add all of this up and form our answer, we're going to have one giant matrix C1x11 plus C2x12 plus all the way through C sub n x1n. That'll be the first row and first entry. And then C1 x21 plus C2 x22 plus C sub n x2n. So here we get our solution matrix written in this fashion. This matrix here can also be written as the product of two matrices. Do you guys know what those two would be? This is a n by 1 matrix. I mean, it doesn't look like it, but this is just one entry. Same here, same here. So we have n rows, 1 column. What size matrix would this be? How do I get an n by 1? And this has to be something by 1, right? Has to be n by n. So this has to be n by 1. Okay? Well, what do you think? What can we put in this matrix? What can we put here so that when I multiply it out, I get exactly this? Undo the dot product, right? Put all the x's in this one. So then in here we would have C1, C2, C3, right? Good. So this is just x11, x12, x1n, x21, x22, x2n, and so on. xn1, xn2, x sub nn. So now we bring in the definition. The fundamental matrix of a system in our context, which we call phi of t, is, maybe I'll just do this. This one. Okay? Which then means that the solution for the homogeneous system x prime equal to ax can be written as x equal to, and we just call this phi of t, times c, where c is an arbitrary n by 1 column vector of constants. So back, again, I keep referring to the same example. Refer back to the only example we've talked about, where we had x1 equals 1 negative 1 e to the minus 2t. x2 was 3, 5 e to the 6t. These were a fundamental set, linearly independent solutions of x prime equal to 1, 3, 5, 3x. We would say that phi of t would be what matrix? What would our fundamental matrix be from this scenario here? It's going to be 2 by 2, right? All we're essentially doing is putting in your x1, your x2, and that's it. So x1 would be e to the minus 2t, negative e to the minus 2t. And then your x2 is 3 e to the 6t, 5 e to the 6t. Okay. Almost done. Any questions on how we arrived at this notation and where the fundamental matrix comes from? Okay. Now, what we need to know is that fundamental matrices have inverses. We know that because the determinant of the fundamental matrix is the same as finding the Wronskian of those solution vectors. And if we know that the solution vectors form a fundamental set, then we know that the Wronskian can't equal 0 for every t in the interval. And thus, since the determinant is not equal 0, then we know that the inverse of the fundamental matrix exists. Okay. There is something also called a special matrix. In some instances, we may want to find an n by n matrix, which we're going to call psi of t. Satisfying a unique set of initial conditions. That's why we call it a special matrix. And those initial conditions produce a matrix that looks like this: 1, 0, 0, and so on. 0, 1, 0, and so on. 0, 0, 0, and so on, 1, which we call the identity matrix. Okay? So this is a very particular circumstance where maybe we have a given system and we want the initial conditions to actually satisfy the condition that when we plug in our initial value, we get an identity matrix. Here's what it looks like. Find the matrix psi of t satisfying psi of 0 equal to the identity matrix in the previous example that we've been looking at, which is x prime equal to 1, 3, 5, 3 times solution vector x. Okay, so from before, and again, tomorrow, well, when do we do 8-6? Monday? Or Tuesday? When we actually finish the unit on Tuesday, you're going to be finding the solutions on your own first, and then maybe going the whole 9 yards and finding the matrix that would produce this identity matrix with the initial conditions. Right now, we already know what the solution for the system is. Okay, so we know that the general solution was x equals c1, 1, negative 1, e to the negative 2t, because they said, here, prove this, and we did, and so we're going to pretend that we already did all the legwork, and that's what the solution to the system is. So now what we'll do, if we want the identity matrix as an initial condition, we notice that t has to equal 0 to produce that. So when t equals 0, I'm going to go ahead and plug in all these values and see what I get. I get c1. If I plug in 0 into t, this becomes 1, so I just get c1 times 1, negative 1, plus C2 times 3, 5. And then now, what does that have to equal? Well, let's put it this way. How big should our matrix be at the end? Almost 2 by 2. So these are column matrices, right? So how many columns do we have in the identity matrix that we're looking at in this case? If this is a 2 by 2 system, then we basically have 2 columns, right? So basically what we do is 2 different equations. Plug in 0. One of these should produce the first column, and the other should produce the second column. So one has to be 1, 0. The other has to be 0, 1. If we had a 3 by 3, we would have C1, C2, C3, plus, the column vectors would have 3 entries, and then you'd set them equal to 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Okay? So this is how you set it up. So let's see what happens. We get C1 plus 3C2 has to equal 1 minus C1, so I'm looking at just this case right now, minus C1 plus 5C2 has to equal 0. Do you guys see how I'm getting those? So let's solve. What does C1 and C2 have to be? C2 is 1/8. We're taking his word for it. What's C1? 5/8. Okay. So, in one instance, we have 5/8, 1, -1, e to the minus 2t, plus 1/8, 3, 5, e to the 6t. Now we repeat the process, looking at the second set, which gives us the 0, 1 column. Here we get what 2 equations? C1 plus 3C2 has to equal 0, minus C1 plus 5C2 has to equal 1. So C2 here is, again, 1/8. C1 would be -3/8. So then our second set, we get -3/8 times 1, -1, e to the minus 2t, plus 1/8, 3, 5, e to the 6t. Okay? So here we are. And now we just put it together. So what's psi of t going to have to be? First entry, 5/8 times 1, e to the minus 2t, plus 3/8, e to the 6t. Second entry. Actually, let's do it this way. This is probably easier to write it down. Think of these as columns. So another column vector v1, another column vector v2. And then that's really what you're going to do. You just kind of write them. So for the first entry, you just go 5/8, 3/8, and then now you do negative 5/8, e to the minus 2t, plus 5/8, e to the 6t. So this is our first entry, this is our second entry in the first column. And then now to complete it, you use your second set of solutions, and that's going to be your second column. First entry comes from the first row, so that's going to be negative 3/8, e to the minus 2t, plus 3/8, e to the 6t, and then now positive 3/8, e to the negative 2t, plus 5/8, e to the 6t. And again, the whole point of this was that this satisfies what? That psi of 0 equals what matrix? The identity matrix. So it's very easy to check, I would imagine, right? Do we get the identity matrix if you plug in 0 in all the entries? Right? Plug in 0 here, you get 1. Here you get 0. Here you get 0. Here you get 1. Okay. The entries. So this entire solution from the first equation, here's how we can think of it. These are equal to columns, right? So when you do this set of systems to get the column 1, 0, your answer is going to represent a column. So first number is going to be 5/8 times 1 and then 1/8 times 3. So that's where I got the 5/8 and the 3/8. Does that make sense? And then the second number in that column is going to you just go down in the bottom entry now. So negative 5/8 and then 5/8. And that's how we got this spot. Does that make sense? And then similarly, for the second column, which gave us 0, 1, we look at our second solution and just go straight across. First entry will be just the top coefficients and then bottom. Okay? All right. We're done with A5. We have one more section to do.